so that you can see what's going on. If you miss a point, you can review it, and etc. And one more thing. Yes, good. Yep, so let's go back. Every computer is just a little bit different. It's very interesting. So on this one, I have to find my pen. So let's have a look and see. Where would my pen be? There it is. So I'm going to go to pen. I've got to ask for it, and there's my pen. Okay. So it's going to be more of the same in terms of we're going to be looking at similar situations of planes flying and blocks sliding and the like. And what they're trying to do in the book, I know exactly what they're trying to do. They're trying to ingrain it so that you think less and less like Aristotle and more like Newton. That's what they're trying to get us to do. So let's go through this. So, and the first thing we're going to talk about is they want to form the link of forces cause acceleration. We're used to the idea that forces cause motion, but in fact, we live in a friction-filled world, so that when we apply a force, there's usually a friction force that's cancelling us out, either completely or largely. So under all circumstances, we need a forwards-facing force to keep us moving, to balance out what friction does. But in most of the universe, there's no friction. So in most of the universe, you don't need... in most of the universe, you don't need something to overcome friction because friction's not there. Now, for us, what we say is that the net force, so the overall force, if there is an overall force, that's taken into account. Yes, you might have an applied force. And yes, maybe there is a friction force. But if we take that into account and we just vectorially add these two guys together, and we do end up with a little F net. So this applied force was just a bit longer than the frictional force was. So there is an F net. If there is an F net, then that must equal MA. So it's not really F equals MA, it's F net equals MA. Any object that accelerates is acted on by a net external force. The net external force and the resulting acceleration point in the same direction. So if I have a particle in space and I have a F net in that direction, then there is the acceleration in that direction. Now, this is again a bit subtle. Acceleration is not the same as velocity. If we're standing still and we have an acceleration in that direction, then we will start moving in that direction. But let's say that we were traveling in this direction. Maybe our velocity is like that. What does our acceleration do then? It modifies our motion, so we'd go like that. So our velocity, because of the acceleration, would look like that, whereas our velocity without the acceleration would look like that. So you can't link acceleration with direction of motion. That's more complicated, but you can link acceleration with the direction of the net force. So you look for the net force and you know the direction of the acceleration. You look for the acceleration, you know the direction of the net force. And it's linked by this equation. This is F equals ma. Newton actually didn't write F equals ma. He had a more complicated version of it to do with momentum, but what he wrote boils down to F equals ma. And so if I plot, let's have a look. My force is F, and my acceleration is here. Then what I find is that, let's say, it looks the same, but it's slightly easier. If I say, here's F and here's M, and it's a straight line, so if I double F, if I have a certain, here's A. Here's the force and here's the acceleration. If I have a certain force, I have a certain acceleration. If I double the force, I double the acceleration. If I triple the force, I triple the acceleration. If I quadruple the force, I quadruple the acceleration. That's a nice straight line that goes through the origin and goes on. Whenever in science you see a straight line, you ask yourself, what does the slope mean? And for this graph, the slope is equal to m, the mass. The slope is equal to the mass. So that raises the question about what is mass? And mass is really quite an abstract thing. We think of it as how much something weighs. That's how we get introduced to it. But in reality, you can take this object into space and it weighs nothing. You know, got to go a long way away from Earth. But you go interstellar space, it weighs nothing. It's still got mass. So it's not a good idea to think of mass as being the weight, because they are really different things. And from a chemist's point of view, I was always taught that mass is how many atoms are there and all that kind of stuff. And yeah, that reflects it, but it really is quite abstract. It's really this slope of the force versus acceleration graph. It's a measure of inertia, like Galileo said. It's this mystical thing called inertia, this reluctance to change your speed or direction. That's what mass is really about. So F equals ma sounds easy, but we'll apply it. So we say you push a crate that sits on a smooth floor and it accelerates. So there's my visualization. I have a force, I have acceleration. So is it subject to a net force? So what do you think? I'm going to get this clicker going, and just you turn the thing on, you go on, and then you pick your number. You can change your mind as time passes, but you pick a number. So do you think, yes, it is subject to an external force, or no, it's not subject to an external force, or maybe, which is it? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So, and here's a tip. I don't know who votes what. So there's no need to be shy about having a guess. And I know some people just don't like to do these things, and they kind of go, I'm not doing it. So if I'm waiting, if I see a person's not clicked, I like to wait for them. But if you're not going to click, they'll be waiting forever. So if you don't want to play the game, just click something, and you're out of there. And we're not waiting for you. But I can't tell what you say, so it maybe makes no difference. I'll give it for another 10 seconds, and then we'll call it a day. I don't want to leave people behind, but I want to get on. So what we're going to say? What do you think? It's going to be balanced, or is it going to be? Oh, everybody's got that. Good. Yes, and that's the answer. Yes. If you have a net force, you have an acceleration. So we're kind of happy with that. So let's put a circle around. Yes. If you applied 4 times the net force, how will the acceleration change? Will it be 4 times greater, 4 times less, or do you need more information? So what do you think? 4 times greater, because it's 4 times the net force. Is it 4 times less, because it's 4 times the net force? Or is it, well, I need a bit more information about this. I need the mass of the object, or something like that. And it's going quite fast, actually. And then 19 last time. We'll give it until 30 seconds, and then let's see. Okay. So what's everybody saying this time? Vast majority of people are saying A. There's a person saying C, and the answer is A. Actually, yeah. You know, if it's F net is equal to MA. If M doesn't change, there was nothing about M changing. If I double F, I double A. If I triple F, I triple A. If I 4 times F, I 4 times A. So yeah, 4 times greater. If it's 4 times greater, it's 4 times greater. If you apply 6 times the net external force, how will the acceleration change? And we did so well in that last one. Let's just go to the chase on this one. It's going to be 6 times greater, isn't it? Yeah, 6 times the force is 6 times the acceleration. You push a 6-kilogram crate, that sits on a smooth floor. Smooth floor means no friction. There's no retarding force. With 3 newtons, what is its acceleration? So let's have a look. Let's do this first one together. So we say, well, F is equal to MA. And at the beginning, at least, I like to put down net down so that I keep reminding myself it's the net force. And let's have a look. This is a 6 kilogram cart, and I put my masses inside the blocks because it's a shorthand way of saying what it is. I actually like to put the forces always pulling. That's just my habit. But this is pushing, so it doesn't matter. This is 3 newtons. And I say, well, F net, are there any other forces that matter? And this is where physics can be a little bit, it's like when you know very little, it kind of seems really obvious, and then when you get more information, sometimes it seems harder. But you go through that, because some of you might be saying, well, yeah, there are more forces. There's my weight, and I know my weight is 60 newtons, so shouldn't I take that into account? And so here's the issue with that. The reason why this thing doesn't accelerate downwards is because there's a supporting force or a normal force, and this is going to be 60 newtons upwards. So those guys cancel each other out. If they didn't, you would accelerate vertically, and you're not. So I don't even have to talk about them. It's not that they don't exist, but they don't matter for this question. And so I'm looking horizontally, and I say F equals MA, so I'm going to say, let's call the positive end, let's call that end positive and this end negative. So I go plus 3, because it's pointing towards that end, is equal to my mass, which is 6, times my acceleration, which I don't know. So my acceleration is equal to plus 3 over 6, which equals plus 0.5. And the units are meters per second, every second. So you can have meters per second, or you can have meters per second squared. So that's what I'm doing. I'm just being careful. I'm just being careful to visualize, because later on maybe things will get more complicated. I need to pick the right force for the right direction. So let's look at this next one. You push a 10 kilogram cart that sits on a smooth floor with 2 newtons. What is its acceleration? So no diagram here. So the first thing I'd do is draw a diagram. And I'd like you to have a go at that, please. So you have a 10 kilogram cart, and you got it being pushed with 2 newtons. So what would that be? And so we'll do a little diagram. And that was 10 kilograms. And this has been pushed with 2 newtons. See if that helps. Give you another few seconds to so write down your equation and then shove the numbers in the right place. There's one more. Good.
Do we do it on the clicker question?
I'm sorry?
Do we do it on this and send it?
Yeah, I'm sorry, you just say on, and then you press whatever letter you think it is. Cool. Well done. Good. So let's stop there. I got 19 again, so let's look. Mainly A, couple of B's, but mainly A. So let's see how that plays out. So I got my diagram, and then I say, well, yeah, according to good old Newton, F net is equal to MA. So I look at my diagram and I say, well, I've only got one horizontal force, and that is 2 newtons going to the right, so let's call it plus 2. And that equals 10 times A. So A is equal to plus 2 over 10, which equals plus 0.2 meters per second per second. So my answer for that one is going to be A. Mainly A, good. And then you push a 3 kilogram crate that sits on a smooth floor with 12 newtons force. So let's have a look. We did pretty well on that one, so let's look at this one. So we'll do this one together. So it's going to be a 3 kilogram, and it's pushed with 12 newtons, and it's on a floor, so let's put the floor in. So I say F net is equal to MA. So look at my diagram, and I go plus 12 is equal to 3 times A. So A is equal to plus 12 over 3, which equals plus 4 meters per second. Agreed? Everybody agree on that? So that's simple. Let's do it. Okay. Jumbo jet cruises at a constant velocity of 1,000 meters per second when the thrusting force, I put on the diagram so you could see where that direction was, of its engines is a constant 100 newtons. So there's the setup. I'm being a bit kind here. I told you it was a constant velocity, so V is constant. Now, what that means is, I told you that the acceleration equals 0. If it's not changing, it's not changing. Okay, so I'm giving you some information there. Without actually saying it, I'm telling you something. And then it says, what is the acceleration of the jet? So my advice is simplify. And you say, do I have a mass? A jumbo jet cruises at a constant velocity of that when the thrusting force of its engines is a constant 100 newtons. So that's going to be 100 newtons. Before I had it been pushing from the back, and now I've got it pulling from the front. I prefer to have my forces like that, but there's no physics reason for it. It's just I like to have the arrowheads going away from the mass. I got a problem here. No, I've not got a problem here. I'm not thinking it through. So can you answer this question? So can you tell me? I think I just gave the answer away a little while ago, but it doesn't matter. Let's see if you can get it. Can you tell me what is the acceleration of this jet? Don't overthink it. Just look at the basic information. Because I was overthinking it. I was trying to do a calculation, and you don't have to do a calculation because it told you the answer. In fact, I told you the answer. And I've been doing this for 20 years, and I just worked myself into a bit of a corner because I was overthinking it. So you got to recognize when it's time to step back and say, hold on. I'll just give it a couple more seconds. What do you think? Want to know what A is? What is A? So let's stop it and let's have a look. What did people say? Yeah, most people are saying it's A, which is 0, and sure enough, that's what it is because it is a constant speed. So there's one of those little cases where I tell you the answer using words. Constant velocity means acceleration is 0. There's no change in velocity in time. So although I didn't use the expression for acceleration, I told you the answer. And I even went so far as even in my talking about the question, I actually even talked about it there. So it's not always going to be. It's not always going to be a calculation. Sometimes it's just going to be reading and knowing the answer from there. But when there's no change in velocity, when the acceleration is, when the velocity is constant, it is a constant. It is 0 acceleration. Right, this next one. What is the force of air resistance on the jet? So this diagram is a bit more. So here's my object. I don't know the mass, and that was worrying me before. But as long as I'm not asked a question where I need the mass, it doesn't matter that much. So ask yourself, what forces would be acting on this jet plane? There's the weight, and there's the lift. Let's call it F lift. There's those two, F weight. And then, well, maybe there's another force. And that would be F air resistance. What's another name for air resistance? What might you call it? Short word, begins with D. Drag, yeah. Could be called F drag. Use the terms interchangeably. So, all right, so there's a diagram. So now, can you get me a value for that? Drag force? I'll stop at 30 seconds. Yes, okay. And what most people, there's only 2 answers here. Because it's, I understand entirely, because I put down C and D. And some people said, poor old Bonaquisti, he meant to put A and B down. And other people said, I'll take him at his word and put down C and D. So that's why it's like that. And if you notice, B and D are large and A and C are small. Okay. So most people are saying this answer down here, I think, yeah? And let's have a look at it. Well, we know there's no acceleration, so that means there must be no net force. And if there's no net force horizontally, I have, the sum, I'm going to do it mathematically, the sum of the forces equals F net equals MA, which equals 0, because we know the acceleration is 0. So that must mean that plus 100 added to, well, this is going to point in the negative direction, minus F drag, F air resistance is equal to 0. So F air resistance must equal 100. It's that guy. Yep. Now, I did something funny with my sign there. I said I know it's negative. And so I got a positive answer. And sometimes people get confused and go, well, suppose I didn't know it was negative. Well, you get a negative answer, it would say, it's in that direction. It's in that direction. So in both cases, it kind of guides you. But sometimes people can get a bit confused about that. But other people could turn around and say, it's an equilibrium. There's no acceleration. It's an equilibrium. Therefore, these two guys must balance, and therefore it is 100 newtons. And there's nothing wrong with that. I'm not saying this is what you have to do. I'm saying some people feel more comfortable when they do it. But if you on the test, you can just see, it's 100 in that direction. That's perfect. That's fine. So, okay. So, and that was actually so that is Newton's second law, because we've got accelerations kicking around. And this was back to Newton's first law, because everything was in equilibrium, if you think about it, yeah? I want to introduce friction. So friction is that resistance to motion that's caused when one surface rubs against another. And it depends a lot on the two surfaces. It's not dependent on one surface. You can't say, copper is always smooth and frictionless, because it depends what it's rubbing against. So it's a bit empirical. There's no way that without doing an experiment you can kind of predict. It's not got much to do with smoothness, actually. If you take, do you know what a watch glass is that is used with a light microscope? Do you know what those are? It's like a very thin sheet of glass. Its idea is you can keep something squished. And so you put a flower between, you can shine light through, and you'll see the inside of the flower and stuff like that. Yeah. Very well made, but thin pieces of glass. If you get two of those and you just put them face to face, they will drag. They will not go over each other, and yet they're incredibly smooth. On the other hand, when I worked in my first job when I was 16 was I worked in a woodwork factory. I did it in the summer. And my job was literally to pick up pieces of wood and just stack them. That was my job. It was like I would watch the sun shine. There was a shadow caused by this lamppost outside the factory, and it would be pointing all the way to the left when I got to work, and it was pointing all the way to the right when I went home. And I'd watch this thing just creep by. If ever you want a reason to stay in school and get a good job, this is it. Because I even got to a stage where I could count how many pieces of wood I could pick up before the clock clicked to the next minute. And it was like, and I just went on and doing it. And my boss, who just sawed the wood and it would fall, and sawed the wood and it would fall, he was too busy thinking about what he was thinking about to talk to me. We couldn't hear each other anyway, so it was a real boring job. Part of what they'd do every now and then when they got bored was they'd send me round the factory on some wild goose chase. Like they sent me to find the plywood counter, and I was the plywood counter. It was like, there's no such thing as a plywood counter. I went around oh yeah, you want the plywood counter? Oh yeah, Joe's got that over in that shed. So I'd go across, is the Joe around? Oh yeah, what do you need? I need the oh yeah, who did we give that plywood counter to? All around the factory. They sent me to this one shop where all there was this ladies. In those days, they used to separate the men from the women quite a bit, actually. So they went me to this shop with all these, they were like my mum's age. And I walked in a brand new set of overalls. They were clean and everything. And I was 16, and they just, teased me like crazy. And I didn't take it bad, so I laughed. And then I was all right. And in a way, it was introduced me to the entire factory. So the main thing was you couldn't get angry. They were making fun of me, but it was okay. I mean, I'll do the same when somebody else comes along. It was like hazing without violence, And but so later on, I'm pushing this pallet of plywood, and it's the weirdest thing because you have this dolly that its wheels go underneath and you pull it, and it's working on wheels. But then somebody needs to use it. And they said, let me borrow the dolly. And I said, I've got to get it all the way over there. And they said, this other person said, let me show you. So they took the dolly away. So my plywood was on these two runners, these two rails, like a sled. And the guy just got his foot behind it and he pushed it across the floor. And he could move this entire pallet. And he couldn't do that on concrete. He did it because that part of the factory was really old, and it had cobblestones. And so the cobblestones looked like that. And for some reason, maybe the sled wasn't touching very much, but it would just slide like crazy. But if they'd done it on concrete, he would have had a tough time with it. So you can't, it's not roughness. It's to do with the nature of the surfaces that's important. So what we say is, when surfaces slide or tend to slide, they might not be moving, but they want to move over one another. A force of friction acts. The friction force is in the direction that opposes the tendency to motion. So if you're pushing to the right and you're not moving or you're not accelerating, or even if you're accelerating but not as much as you should do, there's be a friction force tending to cancel out what you're doing. Even if you're not moving, there'll be a friction force balancing you. We divide the world up into friction when you're stationary, and we call that static, and friction when you're moving, because they are slightly different. The friction force while sliding is called kinetic friction. Is less than the friction force when stationary. Where does that come from? It comes from an experiment. What they did was they took a block like this and they applied a force and they measured the friction force. They used some system. What they did was they found that, got to find my pen again, sorry, my pen tends to disappear on me. What they found was when they had a little applied force, they had a little friction and nothing moved. So then they went to a bigger applied force and they had a balancing friction force and nothing moved. Then they went to a bigger applied force and there was a balancing friction force and nothing moved. And they went to a bigger applied force and there was a balancing force and nothing moved. Then they got to this point here, this force here, and they went a smidgen more and all of a sudden everything started to move. And not only did it move, but when they measured the friction force, it was less. It was less than it had been when this thing was stationary. That's amazing. So static friction can be stronger than kinetic friction can be. And it's found over and over again. There's no question about it. And what's the reason for that? And you can talk to different people and they'll give you different reasons. So a way I think of it is, I think of it as, here's the underside of the block and here's the overside of the table. And there's these peaks kind of hit into each other while it's moving. So this one peak sticking down will hit that peak sticking up, and you'll get a little drag. So that's kinetic friction. But when you stop moving, or before you start moving, what happens is this top piece settles into the bottom piece. And so it finds a better fit. Now there's more of an overlap. There's less overlap here. There's a lot more overlap here. So to get this thing going, I've got to push it so hard that it actually climbs out of the valleys. And so that climbing out of the valleys is kind of that bit there. This is having to push it so hard that it climbs out of the valleys. Now, a materials physicist would say, no, that's nonsense. They'd say every object rests on 3 points. So although it might look like this phone is resting on a big surface area, in reality, 3 points of that case rest on 3 points of the table, because you don't need a fourth point. So the pressure at those points is so great that you form a weld between the bottom of the phone and the table. So there's a weld there, and a weld, it's called a cold weld because you didn't melt anything. It's a better force, more attractive force than is normal. And if you want to get going, you've got to break those 3 welds. And that's what this bit is. This is breaking those 3 welds. There's still the, rubbing up, the rubbing into each other. That's this bit down here when there's no welds. But this extra bit there is caused by these 3 welds. And, it's kind of like just different ways of seeing the same thing. But realize that if you are stationary, the force you need to get going is higher than the force you need to keep going at constant speed. The kinetic friction is less than the most extreme static friction. So we say, well, the magnitude of the friction force depends upon the nature of the surfaces, copper and PTFE, or brass and bismuth, or stainless steel and glass. It's like, depends on those two, if you like, chemistries. But it does not depend upon the speed of sliding. Once you're sliding, it doesn't matter how fast you go. And does not depend upon the area of contact between the two surfaces, because there's only 3 welds. And I got to say something about that. Do you find that believable, that the area does not have any effect? And if the answer is yes, I got to say, have you ever moved a carpet? And if you moved a carpet, what was the first thing you did? Oh, a big carpet that you couldn't actually physically pick up. What would you do? If you went to a room and if this thing was covered in carpet,
Roll it up.
Yeah, roll it up. And then you drag the rolled up piece of carpet, yeah? And that is because I think a flexible carpet has many points of contact, because it can, whereas a rigid object has 3 points of contact, because there's only 3 bits. You touch on one leg, you touch on the other, you touch on the third, you're done. But a carpet will just touch and touch. So I think that this is true for rigid bodies, but not everyday, day-to-day, flexible bodies. Okay, so there's a little bit. Know this graph. This graph is like really important to me. Know this graph, okay? And so we say, did I miss it? No, I didn't. So then I say, okay, application of static and kinetic friction. If you want to slide a box across a room, you have to push hard to overcome static friction to get the box moving. and then you ease off and just match the lower kinetic friction force to maintain velocity. You push, and then you can slide. It's like, it's kind of makes sense. Here's the thing that is really interesting. When driving, if you lock your wheels, it's the worst thing you want to do. So you're driving along the road. How often do you see? You see these big tire tracks on the road? Yeah? That's somebody who's not braking well. They're panicked, and they've locked the wheels. Because when you think about it, it's a weird thing, but when I'm driving, my tire does not slide across the road. It rolls on the road. And that's a bit like putting down my tire, and then putting down my tire, and then putting down my tire. It's like there's one bit of my tire, and there's the next bit, and there's the next bit, and there's the next bit. And it's like a tank track. I'm putting down that first bit, there's that bit put down, and then I roll it. So I lay this bit down, and I roll it, and I lay this bit down, and I roll it, and I lay this bit down. So every bit of the tire gets put down from above, and then it gets lifted up. So that's not kinetic friction, which is one surface sliding across another. That's static friction. And if you think back, the maximum static friction force is always higher than the kinetic friction force. So if I can get my wheels to not lock, but be on the edge of locking, it's called the point of slipping. If I can be on the point of slipping, I'm there. And that's the frictional force. This is FF. That's the frictional force that I am applying to my car. But if I lock my brakes so that I slide across the surface, then I'm somewhere in here, and it is a lower frictional force. So when I was a student driver, this was before they had anything like ABS braking systems. I was always taught you pump your brakes. If you're in an emergency situation, you put both feet out, and you know. But if you have time, you pump your brakes, and you squeeze, and you feel it begin to go, and you take your foot off, and then you put your foot back on. You're trying to ride that bit where you're just on the edge of slipping. Nowadays, of course, we have ABS brakes, and what the ABS brakes does is it monitors your wheel. And as soon as you're moving, but your wheel's not moving, it takes your brakes off. And sometimes, has anybody had it where you press really hard on your brakes and you feel the brake shudder? You break that shudder against your foot. It's basically it's doing the ABS brakes for you, because it's kind of saying, no, I'm not gonna lock the wheels. I'm not gonna lock the wheels. I'm not gonna lock the wheels. The danger is for people like me, where I was taught to pump my brakes, because you're not supposed to do that with ABS brakes. You're supposed to let the ABS brakes take over it. So what happens is you get to about 60 and you start saying, I don't need to be there in 5 minutes. I'll just go a bit slower, you know. So you try to avoid those situations where you're needing to pump your brakes, but it happens from time to time. So just watch out for that. Watch out for locking your brakes. If you lock your wheels, you slide, you leave this big tire track, and you're not the most efficient stopping. You will go further before you stop once you lock your wheels. So also when driving, you lock your wheels. The friction between force produced by your sliding tires, kinetic, is less than the friction force produced by your rolling tires. If you lock your wheels, you have less stopping force than if you keep them rolling. So it's an interesting situation. It's counterintuitive, but that's the way it goes. So what is the net force? Does this sliding crate experience when you exert a 110 Newton force to the right, and the system responds with a kinetic friction force of 100 newtons. So what do you think? Let's just do it real quick. So what do you think? Try not to rely on my diagrams, because my diagrams are usually not so good. So let's call this my F applied. And this is my FF. And get used to, on a straight line, get used to saying that's the positive end and that's the negative end, because it's always good to remind yourself, because you're not adding up arithmetically, you're adding up vectorially, so the signs count. And it says, so what do you think it would be? I got 12 people. So I'm looking for a number and a direction. And again, some people can just look at it and they can just write down the answer, and other people, they want to do the math. So I'm going to stop you in 3, 2, 1. Stop. What do people say? Mainly A, a little bit of B, a little bit of C. So let's have a look at that. So if I was looking at this, I would say, well, hold on. It's 110. So this is 110 newtons to the right. That's positive. And this is, 100 newtons to the left. So let's call that negative. And I would say F net, which equals the sum of all my forces, is equal to plus 110 added to minus 100, which equals plus 10 newtons. And that plus sign means to the right, because it's at the right-hand end of my wire, and right-hand end of my road. So that would be A, 10 newtons to the right. 10 newtons to the left, you'd need a bigger frictional force, and you can't actually have a bigger frictional force than that, so not so bad. Okay, bit of a line. So let's draw ourselves a bit of a line. And we're going to now talk about mass and weight. We've kind of been here before. Mass is not the same as weight. Mass is measured in, what's the unit for mass, by the way? Oh, it's down here. Mass is measured in kilograms, and weight is measured in newtons. So we say mass, kilograms, is a measure of the inertia or the sluggishness that an object exhibits in response to any effort made to change its state of motion in any way. And weight is the force of gravity acting on an object. They're really quite different things. Weight only works in the direction of gravity, but mass works in all directions, so they're very different. You would find it easier, so here's the example. You would find it easier to hold up a cart on the moon, where gravity is 1/6. So 1/6 the gravity means 1/6 the weight. You're just as strong as you were before, so this is fine, yeah? You would find it just as hard to roll a cart forwards to overcome its inertia on the moon as on the earth, because inertia is inertia. And if you're trying to get things to roll, if you're trying to apply a force, you're no stronger than you were before. And pushing this force sideways is not about gravity. It's about overcoming inertia. So it turns out you'd work just as hard. Rotating things on the moon is just as hard as it is on Earth. But holding them up is the only thing that's easier. Yeah? You can hold things up, but rotating, pushing things just as hard, because it does not depend upon gravity. So let's try these. Does a 2 kilogram iron block always has twice as much inertia as a 1 kilogram iron block? So think about what inertia is. Is inertia about mass, or is inertia about weight? What is inertia about? A whole bunch of people jumping on this. Good. I'm going to stop when it gets to 30. What do you think? So what do you think? And it's not cut and dried, is it? So most people are saying yes, but a fair number of people are saying no. So let's think about this. So 2 kilogram iron block, that's its mass. That's its mass. And if it has twice as, I've got a 2 kilogram one versus a 1 kilogram one. So I have twice the mass. And if I have twice the mass, I have twice the inertia, because inertia is dependent upon the mass. So that would be A is the right answer for that. Does a 2 kilogram iron block always have twice as much mass as a 1 kilogram iron block. Let's just double check on that one. So now, does a 2 kilogram block iron block always have twice as much mass as a 1 kilogram iron block? So this is down to definitions, isn't it? It's kind of like, well, what does he mean by mass and what does he mean by kilograms and all that? And this is part of combing our hair to try and get any little knots or any stuff in our hair. We're trying to just get rid of them bit by bit in a painless way. Let's stop there. So let's have a look. Again, it's mainly A, a little bit of B. So it turns out that, yeah, kilogram is a unit for mass. So if you have 2 kilograms versus 1 kilogram, you have twice as much mass, and that's just the way it is, so that's a yes as well. Does a 2 kilogram iron block always, I'm going to emphasize always, have twice as much weight as a 1 kilogram iron block? So what do you think? Now we're talking about weight. Give it just a little bit longer. 16. I'll give it until 25. 17. Good old 17. Good. Okay. And what's that going to be? Mainly B this time. A bit of A, but mainly B. Well, let's have a look. I have a 2 kilogram iron block and a 1 kilogram iron block. And the trick is that always. So, can somebody suggest an example where you won't have twice the weight on a 2 kilogram iron block compared with a 1 kilogram iron block? What kind of physical situation? Yes, please. Yeah. Yeah, I can put the 2 kilogram iron block on another planet and it's pulled by a different gravitational force and it's not got twice the weight. It's only got twice the weight if it's in the same gravitational planet. It's in the same gravitational field. So now the mass does not depend where either one of these two guys are. You can put one of these masses on Pluto and the other one on Earth and they've still got the same mass. You can put one of these things on Alpha Centauri and one on the Earth and they've got the same, and they've got this, it's going to be the double the mass. You can put it and it'll have double the inertia. But you will not have double the weight. So this is a no. Does it always? No, it does not always. So then, would it be easier to hold up a cement truck on, not meaning robbing it, I don't mean by rob it, by using hold up, I mean physically hold it up. Would it be easier to hold up a cement truck on Earth or on the moon? Which would it be? Yeah, good. Almost there, almost immediately. We'll let this go until about 20 seconds and then we'll... Yeah, okay. And this is going to be most people saying B, and yes, less gravity on the moon means that things have less weight on the moon. So an object will have less weight on the moon, so it'll be easier to hold up. Would it be easier to get a cement truck rolling on Earth or on the moon? And the choice is Earth, moon, or makes no difference. Just going to look and see where we're going next. Let's go for a go to 25 on this one. There we go. So let's look. And let's look at that. And again, did I do the... oh, that's interesting. Did I cancel out last time? I probably didn't cancel last time, so it's probably still running on. So that's my fault. I didn't stop it, I don't think. But anyway. So what would it be? It would be it makes no difference. Because it's just as hard to push something over a surface on the Earth as it is to push the same thing over the surface on the Moon. Weight doesn't help it. Less low weight, you know. No big deal. Okay, another bit of a line. Mass resists acceleration. This is a way of reinforcing this. More mass, the more reluctance you are to accelerate. That's inertia. So we say, push a student on a skateboard and the student accelerates a lot. Push an elephant on the skateboard and the elephant accelerates a little bit. Same force, different masses, different amounts of acceleration. For a given force, the acceleration is inversely proportional to the mass of the object. So this is a bit of equation stuff. F is equal to ma. I can say, well, A is equal to F over M. So I can say, well, A is proportional to, that little fish symbol means proportional to 1 over M. What that means is, if you're not going to mess with F, if you're going to leave it constant, don't worry about it. So just look at these two. If I double M, I get half of A. If I triple M, I get a third of A. So if I have a certain mass here and a certain volume, if I double M, I'll have a half of it. If I triple M, I have a third of it, and so on. So, and then we say, well, Newton's second law, A is equal to F over M, or F equals MA. It's just, they're just going around, just practice, practice, practice. That's what they're about at the moment. So here's a weird thing for you. I have two objects. One is twice as heavy as the other. If I drop them side by side, what happens? Let's have a question of this. I'm going to do this actually. I'm going to go here, and I'm going to go. That's interesting. That's interesting. Just hold on 1 second. That is interesting. There's doesn't matter. Okay, I'll just use a space. I can usually get a piece of paper up. I need to just slightly adjust this PowerPoint. So here's a big heavy object, and here's a light object. Here's a big heavy object, and I let them fall side by side, and you take a picture of them. So many seconds later, they've not reached the ground. In the absence of air resistance, I'm making all these little cadres. What would you notice about their relative position later? Would it be A, that the big falls faster? Would it be B, side by side? Or would it be C, big falls slower? So vote me in on those, will you? Will you vote me in on those? What do you think? You can change if you decided, early on you can change it. But vote me in on those and see what would happen if you got this big concrete block and a little concrete block and just let them go side by side. Think back about good old Galileo, and that's what we're really checking on. What do we think on that? And I got 15. I'm going to let it go for just a little bit longer. Oh, good, I got 17. Come on, 18. Come on. Okay, I'm going to let go. Stop now. Okay, let's see what people are saying. Yeah, mainly people are saying side by side. That's brilliant. I'm so happy about that, because that's what's going on. That's great. So we got Galileo squared away. Okay. Sorry, I need to go up there. So now, it's an interesting thing, though. All objects that free fall near the Earth's surface accelerate at 10 meters per second downwards, but different objects have different weights. A heavy object is pulled by a greater force of gravity than a lighter object. So this is pulled by twice as much force that this one is. So it's amazing how if I turn around and say, Oh, I gotta stop in a minute. That's my timer. So it's amazing. I can continue. Just keep on recording. So it's amazing how if I say to people, "Oh, they fall side by side, so is the pull of gravity the same on both objects?" It's tempting to say yes because they're pulled side by side, but they're not. The force of gravity is twice as big on this one as it is on that one. So how come they fall side by side? And what we forget is the inertia is twice as much on this one as it is on that one. So they don't fall side by side because it's the same pull of gravity. They fall side by side because the ratio of the force and the inertia is constant. That's constant. Okay? So what I'm going to do now, what I'm going to do is I'm going to stop recording.